some more participants to join. So let's give them 10 minutes.
Well, quizzes sounds like a fun activity. Is it always general astronomy or other topics you people like the most?
It's mostly astronomy related topics. I mean, just yesterday we had a quiz on astrophysics in general.
Is it always general astronomy or other topics you people like the most?
No, like it's mostly astronomy related topics. I mean, just yesterday we had a quiz on.
There are interesting echoes. Should mute myself that it's not.
Sorry, there seems to be an echo due to the YouTube video playing.
And it's also interesting because you get a time delay of about 1 second, which is the time it takes for the signal to go to YouTube, gets replayed again. So it's interesting.
Yeah. And yeah, regarding the quizzes, we typically have themes. So before we had something on cosmology and stuff. So we change it frequently.
Do you know if many of your members actually do observations themselves sometimes with like telescopes and such?
We do not have an observing program as of yet, but we are working on that. We haven't been able to interact much due to a lot of constraints recently, but I think we'll start to interact more now.
Sounds like fun. When I was so right now I'm physically in Sweden because it's sort of a New Year and Christmas season. So so January I'm doing a postdoc in Israel, but right now I'm physically in Sweden. So like, and I did in Sweden I did the PhD, and so like I learned that, for example, we have an astronomy community here in Malmö, so which so people, so it was more physical at least, so people were gathering from the same sort of area and sometimes doing observations together and sort of lectures.
That's great.
So it was nice to learn. And there were quite a few events centered on the island of Vienna. So there was once upon a time a astronomer which is called Tycho Brahe. He was famous for discovering supernova, for example. So called Tycho supernova like 500 years ago. So there's like quite a lot of events happening on the island where he lived, which he actually owned. So he there was an astronomer who owned an island with a telescope on it. So like 500 years ago here.
Okay, that sounds like fun actually.
Yeah. Well, but at least today the weather here is really cloudy, so like no chance of observing anything. In fact, there's right now a comet flying close to the sun, so it's a comet called Leonard, and it's a comet which is just about have reached eye visibility, and it's supposed to be visible at least in Sweden after the sunset. And I remember that it will stop being visible because it's going to be well, at least in these latitudes. I mean, maybe it's going to be visible in India, but well, at least here, it's been really hard to see it because of the clouds. And I guess probably actually in India right now is also monsoon season, if I'm not
It's
mistaken.
currently winter, but I think the sky can sometimes be clear. And I think the comet was visible in India. I've seen photos of it. Excuse me. Let me disable unmuting by participants.
Hey Alexey,
Hello.
can I ask you something?
Sure.
What exactly are we planning to learn today or watch or like anything? What exactly is the plan?
Yeah, the plan is to, in short, perhaps to make a big picture of the universe and really how the galaxies formed and where do they come from, and sort of like to just an overall show that there's quite a lot of things happening in the universe at the same time. So that's perhaps the main point of what we talk today.
So, are we going to dig into the mathematics, or it would be just like an introduction?
There's going to be quite very little mathematics, if at all. It's going to be very high level and really just to tell about the kinds of things which are happening. Um, if anybody's interested in mathematics, I'm very happy to point at like for each of the subjects how to where to find more information. But so we're going to touch upon a little bit about black holes, a little bit about the galaxies, a Big Bang, and even life in the universe. But so each of these subjects has quite a large underpinning of like study, and quite big fractions of those are mathematical. I'm happy to point at any of those if anybody's interested.
Okay, thank you.
We'll be starting in about 5 minutes.
Saijaran mentioned that in your community, the people have very different backgrounds, but nevertheless, they're all interested in astronomy, so to say. Maybe I should add that I've been in India only once, and that was in February 2019. There was a conference in Mumbai at the IFR on globular clusters, and it was actually a really nice experience. I met a lot of very, very smart people from India, and well, I mean, it was an international conference, of course. So, but there was quite a lot of locals as well.
That's great. I think a lot of the members will be joining a bit late today, so we'll be starting it about now.
Okay, whenever I'm ready. So, Saicharan, whenever you say go, I go.
Okay, so hi, good evening, everyone. Welcome to I3A's live talk on the Big Bang, black holes, and other astrophysical events in our lives. Today's guest speaker is Dr. Alexey, a postdoctoral fellow at the Technion Institute in Israel. He has recently finished his PhD from Lund University in Sweden and has studied the mergers of giant and compact stars. He's currently working on the astrophysics of stellar interactions. So welcome, Dr. Alexey, and thank you very much for joining us today. Over to Alexey.
Well, Saicharan, thank you so much, and it's I just want to say that again, it's my great pleasure to be talking to you here today. Let's jump into the presentation, perhaps. So I'm going to be talking about quite many things, like Sai Charan said, indeed starting from Big Bang and going down to black holes, galaxy growth, and other astrophysical events. And I'm gonna try to convey or convince you that all these things have some connection to our lives. So when I talk about galaxies, I mean, one of the things I like to show is this collage of the images taken by the Very Large Telescope, which is called VLT at ESO, European Southern Observatory. And this basically shows the diversity of the things which are present out there in the universe. So VLT is a very large telescope in the sense that it's actually almost 10-meter size telescope, which has helped us to take really very high resolution images of different parts of the universe. And each image in here, you can see, I guess you could see my pointer. So each image over here is just taken by the telescope, pointing in some new direction here or there or there or there, and you can really see that there's like a diversity of things happening right now in the universe, or seen right now in the universe at a given moment. So for example, you look over there, you see, for example, Jupiter with you see Saturn with its rings. You look over there, you see, for example, two merging galaxies. You look over there, you see at the Carina, perhaps, like something really strange going on. You look over there, you see some other object. I'm not sure the nature of. So I mean, like, there's quite a lot of things. You could see some star forming regions. So literally, just take the same telescope, very, very powerful telescope. Look there, there, or there, and you'll be able to see really very different things. And these all things are happening, well, in the same universe, obviously, and they're actually quite much connected. So I'm gonna try to draw that connection. And I'm going to draw that in two ways. So one is from inside, so basically from the things we can observe from the Earth, and another one from outside. It's basically about how our models model the universe. So let's start about how we understand the universe from inside, that is to say, from the Earth. So if you look at the night sky, so it can look pretty beautiful. So we see quite a lot of stars. Sometimes there's a meteor falling down there. And yeah, well, we see also this band of light, which people call the Milky Way. And this band of light is actually quite important. I'll come back to it in just 1 second. So, I mean, no matter where you are on the Earth, you could see this band of light in sufficiently dark sky. Nowadays, it's kind of hard to see it near the cities, but if you go far away from the cities, it's quite easily visible. If you go to the mountains and there's no city lights out there, it's really easy to see the Milky Way. Now, if you look from our galaxy somewhere into the sky, we see our other galaxies. They look like this. So there are some disky things out there among the sort of like in the stellar field we see. They look like disks. They are pretty shiny. And actually, if you look deeper into space, well, I mean, let's see. So, I mean, if you zoom in on one of them, we can see, well, a disk of, stars, quite many stars. And if you look deeper into space, we can see actually many of them. So, like, we see that actually everything is filled with these sort of blobby structures, and people call them galaxies. And if you now remember about our own night sky, so the point is that, okay, we see some sort of a stripe like this, but if you look deep into space, we see lots of galaxies like that. And the idea then is that actually, well, perhaps we are located in one of these blobby structures, like disky structures. And what we see is the disk from inside the disk. So in fact, that's how we understand where we are. So in fact, we are on the Earth, we're on the planet close to the sun, and the sun is inside a disk of galaxies and gas and dust. And this disk of gas and dust is called the Milky Way. And then the Milky Way itself is one of the galaxies among many other ones, which are looking like this, or like this. And all these things are together in the universe. So that's the view from the inside, so to say. I'll go a little bit slower through all these things. So for the things happening inside our own galaxy, that's again the picture of the Milky Way. This is the band we could see from the Earth, the band with the stars and with the dust in it and with some gas. So we have tried to actually observe every single star possible in the galaxy. And there's been a satellite called Gaia. So Gaia satellite has been launched in 2014, and it's orbiting the Earth, or more precise, it's actually at L2 point, a bit further away from the Earth, but in the solar system. And the Gaia satellite scans the whole sky and systematically tries to identify and characterize every star it can find. And so far, since 2014, this Gaia satellite has been able to find and characterize 2 billion stars in our galaxy. That's approximately, give or take, maybe 15 or 20% of all the stars in the galaxy. So when doing so, Gaia has constructed, this Gaia satellite has constructed the most detailed map of the Milky Way so far. So essentially on this image, we see all the observations that this satellite has made. So all the 2 billion stars it has observed.
Do you remember?
Each
When I
point
told
on the
you.
image, sorry, each point on the image is a star or a group of stars which is seen by the Gaia satellite. So in fact, the Gaia satellite has, well, collected all the stars it could see and has made this assembled image. And this is
Do you
actually
want me to
the
bring the
picture
pram?
of our galaxy.
Excuse me, Dr. Lex, can you please make me the host?
Yes, sure, no problem.
Thank you.
I'll
Okay.
take the pram.
All right. So continuing onwards, so
Yeah, I'm with him.
so we are there in the Milky Way. We have been able to see stars which make up the whole galaxy, and it looks like this. And this is the view of just our own galaxy. But there have been also instruments which have been trying to make a map of not just our galaxy, but of other galaxies. And next thing we'll see is the video from the Sloan Digital Sky Survey, which was set to actually map all the surrounding galaxies in the universe and actually make a kind of a grand image of the universe. And it looks like this, if I get it to start. Should let me turn on the sound. So Sloan Digital Sky Survey is a telescope which has been looking not at stars in our galaxy, but at galaxies all over the universe. So this is a quick zoom out of what it has been seeing, and the video sequence will repeat it from the sun in a slower manner. So Sloan Digital Sky Survey has been able to measure many galaxies at once and make a detailed picture of them. So right now we're looking at the stars in the solar neighborhood. So that is to say, here is the Earth, and here are the stars which we see on the Earth on the night sky. And it will continue to zoom out and show more and more objects or stars in later galaxies which it has been seen. So this was our solar system. And if we continue zooming out, we see that the stars which form the night sky are only a small fraction of stars in the whole galaxy. And as we continue to zoom out, we see that here is the sun, and here is our Milky Way galaxy, which the Sloan Digital Sky Survey has been able to see. And then if we continue to zoom out and just show all the different objects it has been able to map, this Sloan Digital Sky Survey, we see that our galaxy is located close to other galaxies, and then they in turn arrange together, so they actually fill whole space, and all the other galaxies form sort of like different, well, I mean, it's just a field of galaxies, literally. Some of them are close to each other. Sometimes they form sort of like filaments of galaxies. Sometimes they form something like sheets of galaxies. But altogether, there's really lots of galaxies. And if we continue to zoom out, then we see that there are really quite a lot of galaxies mapped by this survey. So I guess probably it's a good time to stop here. So this Sloan Digital Sky Survey, the reason why we see two lobes is because it's been able to see only some portions of the sky, not the whole three-dimensional space, but only in some sort of conical sections of the sky. But we see that the galaxies really extend to really quite far away, and later the video shows basically the different variety of galaxy types we can see. But overall picture is that, like, there's solar system, there's Milky Way galaxy, but if we keep on zooming out, we see lots of other galaxies, and they form this gigantic big structure of galaxies. So they fill the whole universe. So universe is filled with galaxies, and that's basically pretty much what we see. So this visualization is called, it was made within the VRAP project, and that's basically how we understand the universe the best. There are a few more observations which I'll talk about in a second, but this is basically the view from within, I would say. Now, let's try to see the universe how we see it from outside. In other words, how we see it through the lens of our models and our simulations. So in other words, how do we think this whole thing works? So here is the picture of Big Bang made by myself, and I think that's like the way how Big Bang actually looked like. So the point is that according to the current models of cosmology, the universe started from a very, very condensed, very dense state of extremely high temperatures. To give you a sense, at time equal to 0, at least according to the cosmology models, the size of the universe was a order of the size of a tennis ball compared to the present day size of the observable universe. In other words, all the universe we see today at initial time of the Big Bang was so much more dense, so much more compact, that it was comparable to the size of a tennis ball. And everything was extremely, really hot. Everything was at the very initial times was at extremely crazy temperatures of like 10 to the 30th time to the power of 30 Kelvin. So which means that 1 with 30 zeros of Kelvin. It's really almost incomprehensible temperature. And the universe, extremely hot, extremely compressed, was literally homogeneous. Everything was extremely very bright. Obviously, nobody could exist at that time because it was really very, very dense and hot. We don't exactly know whether it was really infinite or finite. So in other words, whether the size of tennis ball was everything or whether the universe was stretching infinitely. But we know that the observable universe was of the size of the tennis ball. And we know that this whole mixture of material very, very quickly expanded. There was a lot of things happening even within the first nano, micro, and smaller fractions of seconds. But we know that by the time of 10 to the minus 6 seconds, or by the time of 1 microsecond, all the matter was created from energy. And there was quite a few details of what was happening in the universe between time equal to 0 and time equal to 1 microsecond. And I'll skip through that because there's quite a lot of like small details even to go through at even that point of the universe. What we can say, well, is that, at 1 microsecond after the Big Bang, the matter in the universe was made of gas, approximately 15%, and dark matter, approximately 83%. There was also dark energy, which is not included in matter, which actually was about 5 times more contentful in terms of energy compared to gas and dark matter, but dark energy is something which is maybe a bit more disputed, so I'll skip through that. So within the first 10 to the minus 6 seconds, or within the first 1 microsecond, the universe was filled with matter and dark matter. And here is a picture of how we think the universe evolved, and I'll walk you through slowly through this picture. This is an image by NASA, and this image summarizes the history of the universe according to our cosmological models. So the Big Bang on the picture is on the very left, so it's at time equal to 0, and the present day is on the very right over here. And the time goes to present on the x-axis. So in other words, this is distant past, and this is the present. And initially, when there was the Big Bang, so again, the observable universe was about the size of the tennis ball. Then there was a phase of really rapid expansion called inflation, which happened within the first microsecond, which we didn't talk much about. Then the universe was slowly cooling down. It was initially very hot, and then it was cooling down. At some point, it cooled down sufficiently that the temperature of the gas in the universe was lower than about 1,000 degrees Kelvin. At that point, the material in the universe, the hydrogen filling the universe, started to recombine, and the universe became transparent. So at that point, the light started to shine through the universe, and it was not absorbed anymore by the material in between. So you could visualize it that way. So like in the very beginning, everything was really hot, and it was as if the universe was filled by flame. So like if you try to see through fire or through flame, you cannot see much through fire because fire is opaque, so the light cannot go through fire. But once the universe cooled off, the material which was making the fire filling the whole space cooled down, and it was just as if you were looking through air. So in other words, after this time, the gas was cold, and so you would be able to see through the gas, and the gas was just like the air in the room, so it was quite transparent. So at some certain time, the universe switched from this opaque state to transparent state, and then it existed for approximately 400 million years in this state of being pretty much transparent. There was some gas in it, slowly contracting, but there was nothing shining. So this phase was called dark ages. And then later on, after material contracted sufficiently, the first galaxies and stars formed because the gas had to come condense together to form galaxies and stars. So it took some time, so this 400 millions of years. And then once the galaxies and stars formed, the universe was filled with light from the stars, and the gas was ionized, and kind of the universe was filled with light, so to say, from the first formed galaxies and stars. And over time, there were more and more galaxies formed, and more stars formed inside the galaxies. So if you look through time, so we see that, well, there's pretty many galaxies, observable at the present day. And if you look further in the distance, so we see also quite a lot of galaxies which emitted light, and light then reached us. So we see the galaxies from the past. So the universe at present day expands, and it's expanding in an accelerated fashion. What it means basically is that, well, okay, there was this Big Bang, then the universe was as a whole expanding, but the material in the gas was clumping and forming the galaxies together. And what we see at the present day is that the universe as a whole is expanding, but also there are galaxies inside. And if you see how the universe is expanding over time, we see that it's expanding in an accelerated fashion. In other words, galaxies are becoming further and further from each other in an accelerated fashion. We study these things by theoretical models, by writing mathematical models, and by solving equations of cosmology. But we also study these things by running large computer simulations, which help us understand how the universe evolved at each of these different stages, very early on, for example, or later on when the galaxies were forming, or closer to the present day. And I'll show you examples of a few simulations which kind of give us intuition about what has been really happening in the universe at these different stages. So the first simulation is from the so-called Thesan project. The Thesan project looks at how the first stars re-ionized the universe at this very first stage, when the first galaxies formed, and how did the first galaxies shine through and fill the universe with light. So the way it looks like is this. So the gas condenses and forms small galaxies, and they fill the universe. Well, essentially here we see the density of of gas, and here we see the density of ionized gas. So in other words, the blue means that the gas has been ionized by the light from the new galaxies, and we can see this structure, filamentary structure of galaxies next to each other. So I'll play it again and explain from the other perspective. So see, initially the universe was filled with gas, which was really homogeneous. So there was just gas and there were no galaxies. But then quickly over time, the gas was able to condense and form sort of like clumps. And these clumps led to formation of galaxies and stars. And these galaxies and stars then were able to shine and ionize the gas around them. So what we see in this cube is lots of filaments. And these filaments are filaments of gas which has been able to condense, and then in these filaments the galaxies formed, and then the galaxies contained stars, and the stars ionized the whole surroundings. So if you look at it again, we see that there are galaxies forming, filling the universe with radiation. We can see the filamentary structure in the cube, and we can see how the galaxies ionize the gas in between them. So that's basically the sort of things which was happening in the universe in its first billion years or so. So this particular simulation project was really focused on studying how does the radiation from the first galaxies and stars affect the universe. There are also quite many other projects which have been focusing on literally how galaxies formed, for example. So, for example, here in this video, this video is from the Illustris project. We focus on a block on a cube of gas in the universe, and look at how different galaxies actually form. So here in the image, we see how, well, gas is forming into a clump and condenses, and in here we see how the a new galaxy actually forms. So the point is that, well, whilst the gas is attracted to itself gravitationally, it's also not so easy for gas from the universe filling the space to actually fall nicely. It actually falls onto itself or falls onto the galaxy in somewhat of a chaotic manner, and as it does so, it compresses, and still, if you have heard about angular momentum conservation, it has to conserve angular momentum, so it has to kind of conserve its spin as it falls down towards the places where the galaxies form. So there's quite a lot of details in this picture, and right here in the simulation we see different views. So in this case, right now we see the gas metallicity, so the amount of metals of different types, and right now we see the gas velocity, so it's just different view of a galaxy which has been forming in the universe. And right now we're looking at luminosity in a particular band of hydrogen. So there's quite a lot of ways of seeing the galaxies, and if you keep evolving them, so we see that over time the gas sort of settles up, and the galaxies eventually become more and more disky. So this is an image of how this very galaxy looks like. So this is the overall picture. So the galaxies we see today initially formed as sort of places where the gas was flowing in a dense way, and later on over time the gas has been accumulated over time into a disky structure, and now it looks pretty much more orderly. So back in the beginning the universe was like that, lots of gas flowing into filaments, and then over time it was quite messy. I'm skipping over different parts of the video. And then over time later on the galaxies became bigger and more well defined, and now we see galaxies pretty much like Milky Way, how they look today. And of course, in the galaxies, inside each galaxy, there are many stars, as we talked about. So here's another video. That's a video from actually Vintergatan project. Vintergatan is a Swedish word for Milky Way. This particular video is shown with the permission by Oscar Egerts, and it's a video which has been created in Lund, where I did my PhD. And I should just say that this particular video has been aiming at reproducing our own galaxy, how our own galaxy formed this cosmological fashion. So like, how did Milky Way form cosmologically? And here's how it looks like. If I'm able to show it. Yep, unfortunately, for this or that reason, the video refuses to play. But well, apologies for that. But at least the yep, okay, apologies for that. Nevertheless, the Milky Way formed like other big galaxies, although you could see more features specific to Milky Way. But this is just to say that Milky Way formed also like a disk galaxy. It also had gas infall into it. Initially, the Milky Way looked quite messy. Over time, Milky Way stopped looking as messy, and Milky Way galaxy again formed like through accumulation of gas and stars over time. So here we are then in the universe with lots of galaxies created and lots of matter and stars found in the galaxies. And I will zoom in, or I will discuss a few things about these galaxies, and just to try to kind of show the diversity of things which are happening there at once. So first thing is going to be about black holes. So if we come back to observations of our own Milky Way and actually try to look into the galactic center, we will see that actually in the Milky Way there is quite a large black hole in the very center. So this is a video made by the VLT gravity collaboration. VLT again stands for the Very Large Telescope, and here we are zooming in on the stripe of the Milky Way of our own galaxy, and we are trying to actually look into the very center of it. It's called Sagittarius A star region, and I should mention that looking into the galactic center is actually pretty hard because there's a lot of dust in the way, so we actually have to look through dust. So people use infrared telescopes to actually be able to see through dust, because dust absorbs the visible light much more than infrared light. So with infrared light, we can see deeper into the galaxy. And if we try to zoom in into the galactic center, we see that there's a lot of, a large concentration of stars in there. It's called the nuclear stellar cluster. And if we keep on zooming in, we will find that actually there's a region wherein stars are moving in a very unusual way. So actually these are images taken by a telescope over the course of about 10 years, and they show basically that there are stars moving around something really massive. So put in a different way, usually stars do not do many things very quickly. So in other words, typically, I mean, over a course of 1 or 2 or 10 years, the stars just, I mean, most stars in the galaxy don't do anything because the distances are very large and the stars move pretty slowly, so to say. But in this specific region, the stars are actually moving really very quick, and moreover, they're moving very quickly around a center of very large concentration of mass. So specifically, this is an orbit of S2 star, one of the closest stars to the galactic black hole. And the S2 star has approached the black hole within approximately 1,000 astronomical units, which is the distance between the Sun and the Earth. And this S2 star has been mapped by the observations continually over time. And generally, people have been studying the orbits of a few tens of stars which are orbiting the supermassive black hole in the galactic center. And right now we have the orbits calculated for all of these stars, and it basically tells us that all these stars are moving or orbiting around a really massive object quite close to the center of this picture. So, and it is the supermassive black hole, which is approximately which has approximately 5 million solar masses in mass. I'll stop here. And well, apparently in the center of our galaxy, and actually in the centers of other galaxies, there are these supermassive black holes, which are typically of order of between a few million solar masses, and sometimes they can go up to billion solar masses, in fact. And these supermassive black holes have, well, actually their formation is not fully yet understood, because it's not really obvious how does one create, how did actually they form, in the sense that having a very massive black hole requires quite a lot of gas and stars to come into the region where the black holes are, but also the understanding that in detail is quite complicated, because we have to know how the galaxies evolved and how gas and stars came to the centers of the galaxies. And then at the same time, when the gas and stars come to the black hole starts to shine, because the gas and stars get very much heated by accretion to the black hole. So it's actually quite hard to model how did these supermassive black holes form. But we know that supermassive black holes are found in the centers of many galaxies, not all of them, but quite many galaxies, and that they are a part of the galaxy formation history. But again, I just stress that we don't fully understand how exactly they have grown to their masses. But what is a black hole generally? So, like, a black hole is actually an exotic object of general relativity. So here on the image, we zoom out and look at a conceptual black hole as visualized by its effects. So, put very shortly, a black hole is an object which is so dense that light cannot escape from it. So in other words, if you take any object and make it extremely very compact, its gravity will increase stronger and stronger, and because the gravity goes as 1/r², so at some point you can compress the object so much that even light will not be able to escape from its gravity. So if you take the sun and start compressing it, so it will turn into a black hole when the sun is compressed down to 3 kilometers in size or so. So in other words, if you really try and compress the sun and want to make it a black hole, if you are able to compress the sun down to 3 kilometers, you're good. So it's a black hole. So a typical astrophysical black hole has the size of order of, give or take, maybe 30 kilometers. They're typically more massive than the sun. They're typically about 10 times more massive than the sun. The supermassive black holes are about 1 million times more massive than the sun, as I said, or up to 1 billion times. So in other words, they can be actually really very massive. And the black holes are these interesting general relativistic objects. And the point there is that, so general relativity is our theory of gravity, which is the commonly accepted theory of gravity. And put in a very simple manner, general relativity says that the objects gravitate towards each other, not because they create gravitational forces, but because they curve space-time in such a way that it leads to effect which is similar to gravitational attraction. So put in another way, in general relativity, or our common accepted theory of gravity, the effect of masses on the other objects is by them curving space and time, and this curved space and time then leads to gravity. Why I'm saying this is mainly because, if there's a black hole, then there is a mass which does not allow light to escape, which means that it has really very large gravity.